Good morning, everybody. So we're continuing our investigation of statistical physics, statistical mechanics, and well, I will just remind you that what we have done in the previous lessons, we devised the form of the partition function for the case when the different states or the different modes of the system were wave-like modes. So it basically was an integration of e to the minus beta of the energy multiplied by the density of states for this energy, where we use the frequency in order to describe the density function. While we were using this form for the partition function, how we derive it? We derive it by some sort of a mixture of classical and quantum approaches. When I say classical, the classical approach was actually applied only at the stage when we needed to obtain the relation, dispersion relation between the case, the wave vectors, and the frequency, and the omegas. But this form, and more specifically, the form for v prime of omega, which was v divided by 2 pi squared k squared of omega dk d omega, was derived purely on the wave representation of quantum mechanics. Okay, so we have particle in the box. We describe those particles in terms of the wave function, quantum mechanical wave function, and we assumed that everything was isomorphous. So we don't care about very specific directions for our particle in the box. Okay. Now, this is a quantum mechanical representation. What we have used afterwards, this stage was quantum mechanics. What we have used afterwards is to actually write that k of omega is something multiplied by omega, some constant which was 1 over the speed of sound in the material, was the classical part. Now, but statistical physics, and more specifically this notion of partition function, was actually developed way before quantum mechanics was even dreamed of. Okay, it's actually started in 1975. This notion of partition function by Willard Josiah Gibbs, and he wrote the form for the partition function in the following way. So in his case, the partition function was an integral. So it's classical partition function. So in the Gibbs representation, it was an integral of e to the minus beta. Beta was the same beta, 1 over k Boltzmann T. Here stand the Hamiltonian, which is generally a function of x, y, z, and all the conjugate momenta. So px, py, and pz. Here we have dx, dy, dz, dpx, dpy, dpz, and he had a prefactor, 1 over h to the 3rd power. Now this h, right now we know that this h is the Planck constant. When Gibbs wrote this formula, he had no idea about Planck constant, and there was still no Planck constant whatsoever. And for Gibbs, there was some sort of a prefactor, which actually is coming from the notation, that there should be no. He had some numerical value over here. He had no idea what this numerical value is, okay? And his idea was to actually compute this numerical value from the experimental data. Why there should be some sort of a numerical value is exactly why there is a numerical value of beta over here. Okay. So it's this not only the scales, but actually. The ingredients should be unitless. Okay, so it's like over here, it's e to the something which should be without a unit. So beta is 1 over joule. Hamiltonian is joule, so there is no units whatsoever here. Exactly the same goes from dx, dy, dz, dpx, dpy, and dpz. There should be absolutely no units for the partition function. So he had some sort of a numerical value. Now this is the classical form. Okay. How he got it, and why he had exactly this prefactor here is a great physical insight, and we are not going to develop this derivation of Gibbs. But what we actually going to show is that if we start from our notion of partition function, from the quantum mechanical case, okay, and use very simplifying approach, we can actually obtain this classical representation. So originally it was the other way around. There was no quantum mechanics, there was pure statistical physics of classical systems with some numerical values, which is actually a Planck constant. And afterwards, it's actually contributed to understanding that there should be some sort of a different kind of physics instead of classical physics. And the usual way is what was going from this description into this description. Right? From classical physics to quantum physics. What we are going to present, because it's much more simpler, is how to take the quantum physics representation and obtain the classical one. So, how actually I'm going to do this? Well, it is pretty simple. So, what one needs to do is to write this original integral of z for the quantum system. It's an integral over all omegas e to the minus beta of epsilon. Epsilon is my energy, which is a function of omega, d prime omega, d omega. Afterwards, what we are doing is saying, well, there is a pretty much straightforward transformation, not straightforward, but there is a transformation from quantum approach to classical approach, and it goes through the wave. Now, in this representation, h bar k multiplied by the wave vector is simply the momentum of the system. Okay. This is what we are going to use. Energy of the system, which is different states, different eigenstates of the quantum mechanical Hamiltonian. In classical physics, they are transformed to the Hamiltonian, classical Hamiltonian, which is a function of x, y, z, px, py, and pz. Okay, so in quantum mechanics we have operator, eigenstates. In classical physics we have just a function. Right? What else do we have? So if you look on what is d prime omega has this v over here. V is volume. So the volume, right, it's what? It's just an integral over x, y, and z over dx, dy, and dz. Some additional parts that we have over here? Actually, no. Actually, no. So if we plug everything inside, so what we have inside, we have, instead of epsilon of omega, we have the Hamiltonian. Instead of the volume, we have an integral of x, y, z. We plug this guy inside an integral, so we have z equals to the integral over px, py, and pz. I'm sorry. So the integral is over omega, and here we have an integral over x and y and z, e to the minus beta. Instead of epsilon, we write our Hamiltonian, and here we have dx, dy, dz. This is coming from the volume element, divided by 2 pi squared. And still we have this k squared omega dk d omega d omega. We can rewrite this as an integral over k, okay, an integral over k, an integral of x, y, and z. So integral of k, x, integral over y, integral over z, of e to the minus beta Hamiltonian, dx, dy, dz, 2 pi squared, k squared, and dk. Where it brings us? Well, I want to obtain this classical representation. So the integration is in the phase space. Remember, the phase space is defined by the coordinate and the conjugate momentum. So instead of integral over dk, I want to obtain some dp, dpx, dpy, and dpz. So what I'm doing, I'm saying, well, k squared, according to this guy over here, k squared is simply p squared divided by h bar squared. And dk is simply dp divided by h bar. Okay, we plug it into the integral and we obtain an integral over p, integral over x and y and z, e to the minus beta h bar, dx, dy, dz, divided by 2 pi squared, multiplied by 1 over h bar squared, p squared, dp, divided by h bar. Okay, so this is our integral so far. What we're going to do now, we're going to say, what is p squared dp? So it is an integral over the size of dp. But if we are using the notation that p is the size of the vector, okay, in what space? In the space of px, py, and pz. So we can say, well, actually, this guy came from where? This guy came from interpretation that we have, this is a volume element. This is a volume element, so what is our 4 pi p squared dp? It should be dpx, dpy, and dpz. Okay? So we have three-dimensional space, and we don't care about directions. We only care about the size. Remember where all this came from. This came from counting over space. Okay? And the space was isotropic, either in x or either in p. Okay? So we couldn't care about dimensions. The only thing that we cared about is the distance. We calculated the volume in some specific space for the case, exactly here. So if we don't care about the direction, if we don't care about exactly the direction, so this is 4 pi over here is coming from where? Is coming from integration over the two different directions in the three-dimensional space of px, py, pz. This is the Jacobian. We are going into representation of polar coordinates. Okay. So p squared dp is equals 1 over 4 pi dpx, dpy, and dpz. And we eventually obtain that rz is an integral, well, there are 6 integrals of px, py, pz. So it's integral over p, an integral over x. Okay. What we have inside is e to the minus beta Hamiltonian multiplied by 1 over 2 pi h bar to the third power. Here we have dx, dy, dz, dpx, dpy, dpz. Okay. And eventually obtained by recalling what? Recalling that h, the Planck constant, is 2 pi h bar. So we have z 1 over h, which is a Planck constant, integral over p, integral over x, which is a three-dimensional integral, each of them, e to the power e minus beta Hamiltonian dp dx, which is exactly the classical form that was invented by Josiah Wheeler-Gibbs in his 2 papers, 1875 and 1878. He had no idea what this Planck constant is to the third power, I'm sorry. He had no idea what this numerical constant is. He just used it as, well, I have some units over here, and I shouldn't have, because the partition function comes from what? From counting over different states. And he counted the classical states, right? Now, it's not limited only to the x and px and y and py representation. In general form, we can have q's and p's, okay, as our general coordinates, which can be whatever we want, okay, not some specific spatial ones, but the coordinates that define our system. P's are the momenta associated with those coordinates from the Hamilton equations, and we obtain that z equals integral over q, integral over p, e to the minus beta h of p and q in general. Okay. And here we have pi over j, dpj, dqj, divided by h to the power 1/2, divided by h to the power 1/2. Okay. Okay, so it doesn't really matter how many coordinates, this was the form of Gibbs, how many coordinates that we have, and where those coordinates came from. What we actually need to do is to compute the Hamiltonian, take this form factor over here, which is an exponential of minus beta the Hamiltonian, and multiply it by dpj, dqj, so it's basically the Jacobian in our phase space, defined by p's and q's, and divide everything by the appropriate power of the sum constant, which is apparently the Planck constant. Now, this is actually nice, and this is the classical representation, but we can ask a little bit more. What we can ask of it. So, where this guy is actually coming from. Where this guy is actually coming from. So this is, if we think about it, this is an integration in the phase space, and it counts all the different states, right? So the partition function, it goes over all different states that are associated with the system. So for each state, we take this factor, which is e to the minus beta, the Hamiltonian. Multiplied, well, originally we had a sum. And it's very easy to sum up states in quantum mechanics because, well, we have integer numbers sometimes there. This is how we started. But in classical physics, there are no such a thing. There is a phase space. We already spoke about it a little bit. There is a phase space. And in this phase space, what I do is basically take some sort of a size of this phase space. Okay, let's try and plot it. So in this phase space, what I do is I actually have to go let's look on the Q and P. So I'm going over all different P's and Q's that are associated with this form factor, okay? And I count the e to the minus beta h. Now, eventually, what I'm integrating over are those some small portions over phase space, right? I sum up over all different volume elements of my phase space. Right. I go over all different I integrate over all the volume in my phase space. For each coordinate, I multiply it by e to the minus beta h bar pq, and each volume is basically should provide me how many states are in the global volume. Okay? In quantum mechanics, I sum up over all different states. You remember I had integer states, I associated a volume with each of those states, and then I summed up over all those small volumes, and it was just the integration. Here I simply integrate, like Gibbs did, I simply integrate over all the space. Now what this actually means, what is dpj, dqj, which basically the size of this volume element is dq multiplied by dp. But it should give me the number of states. Give me some volume with units, but it should give me the number of states. So I should multiply by the density, right? I should multiply by the density of the states here, and by the density of the states over here, and by the density of the states over there. So the Jacobian, as it's written, let's assume that we have only P and Q. So Z is integral over P, integral over Q, e to the minus beta h of P and Q. Okay, this is a contribution. This is the Gibbs factor. And here I should have rho, the density of the states in specific P and Q multiplied by dP dQ. This is how I count states. For each different state, I should have the density of the states in this region multiplied by the size of the region. Exactly, this is how we calculate the the mass, or how we calculate all different kinds of physical quantities where we're using the continuum limit approximation. Now, in our presentation, what is rho? What is the density of the states? The density of the states, according to this function or according to this function, is just simply 1 over h. 1 over h. So this is the density. And this density is exactly the same for all different positions in our phase space. And what it means, if it's exactly the same, okay? So what we need is what stands here. This is our density. Rho of P and Q equals 1 divided by Planck constant h. What it actually means that there is exactly one state, okay? This is the classical interpretation. There is exactly one state in a very small volume element of what size? Of h bar of h to the half multiplied by h to the half. Okay. So this is something very peculiar from the classical interpretation, because it basically states that there are no more than one state for a volume element in the phase space of the very minimal size. So the continuum approximation breaks at some point. This is what this says us. So if we want to squeeze different states in a very, very small volume, there is a limit. And what is this limit? This limit is when the volume elements that we are looking upon are on the size of the Planck constant. The moment our volume elements are on the size of one constant, of one one Planck constant, there is only one single state per this volume. So if we take those squares over here to be in the size of h to the half multiplied by h to the half, h to the half multiplied by h to the half, there is only one single state per square. Right. And this is our transition from quantum mechanics and classical physics. In quantum mechanics it was clear because we started from the situation that we have only one state, that we are different integer states. And then we somehow integrated over them. In classical physics it's the other way around. We start from an integration, okay? But this integration have a very specific interpretation. This integration have an interpretation that the density breaks down after some specific squeezing up. Okay? So one can think even of this matter as some sort of a representation of the Heisenberg uncertainty principle. Okay? Delta P, delta Q is greater than h bar. Okay? So you cannot basically have, you cannot go and identify a simple state of the system that is smaller than the Planck constant. So all of this was really peculiar. And this interpretation was pretty much peculiar from the classical point of view. It's very clear for us where it's coming from, and it's completely unclear for me how one can imagine that this should be the presentation, because actually the classical representation came up first. And the way is that you have the data, and you have the experimental observations, and when you, not me, not us, but when Gibbs and Boltzmann thought about the proper representation, they made a lot of tweaks, small tweaks. Why they made these tweaks? Well, for me and for you, it's now clear that you should have a quantum representation. For them, it should be clear that the experimental data should fit whatever theory you're devising. Okay? And the data, even already then, showed some specific properties that had their roots in the quantum mechanical representation. All right. So we have this one. So let's now that we have the classical representation for the partition function, let's see what happens for the ideal gas. So we have a gas of particles sitting in a box. All those particles are not interacting. And we want to compute the partition function. Okay. So we want to compute the partition function. So remember, the particles are not interacting, so the partition function factorize. So what we need to do, we need to compute the partition function for one single particle, okay, and take it to the power of n, which is the number of the particles that we have in a box. So we have a box, there is a lot of particles inside. Inside the box, they're doing something, moving in different directions. Okay, their classical representation. We should compute the partition function, classical partition function, for one single particle. Okay. Why we can do this? Well, basically, because it factorizes. If it's factorized for a quantum system, it's also factorized in this representation. The Hamiltonian is simply sum over all different energies of all different particles, and the p and the q's for all different particles are also not related to each other. So what we should do, as we've already previously done in the usual quantum case, should compute the partition function for one single particle, take it to the power of n, the number of particles, and here we have, and we should have afterwards, what we should have afterwards the partition function for the full system. Okay, so we start with the partition function z, small z, let's take it. Partition function of one particle. So classically, what is the function? So it's 1 over the Planck constant to the third power, integral over x, integral over y, integral over z, e to the minus beta, integral over px, integral over py, integral over pz, e to the minus beta. What is our Hamiltonian? Of free particles, right? So it's the energy of the particle. So it's px squared divided by 2m plus py squared divided by 2m plus pz squared divided by 2m. Okay? The particles, it's a classical ideal gas. The particles have only kinetic energy. The kinetic energy is the momenta squared divided by 2 mass per each degree of freedom. So per each velocity. Okay. And here we have dx, dy, dz, dpx, dpy, and dpz. So this is the partition function. First of all, integration over x, y, and z. The only restriction that we have is that it's a box, and the box sums up specific volume. Finite volume V. It's not an open space, an infinite space, it's have a specific volume. So this integration, okay, over the spatial dimensions of the system is simply contribute the volume of the system, because the potential energy or the Hamiltonian does not have any contribution from this. There is boundary conditions, but this is not represented in the Hamiltonian as we were doing. So it is equals to 1 over h to the third power multiplied by v, an integral of px, py, and pz of e minus beta px squared divided by 2m multiplied by e to the minus beta py squared divided by 2m multiplied by e to the minus beta pz squared divided by 2m dpx, dpy, and dpz. And this integral, it's actually multiplications of 3 different integrals, right? Because there is the integration over px, integration of py, integration of pz has nothing. Actually, they are not correlated or not related to each other. The other thing is, what is the possible values of the momentum it can get from minus infinity to infinity? We don't have any restriction on the energy. Remember, it's a canonical ensemble representation. So here we have minus infinity to infinity, minus infinity to infinity, minus infinity to infinity. Okay. So what we obtain is that this integral equals to the volume divided by the Planck constant to the third power. Okay. And here what we get is an integral from minus infinity to infinity, e minus beta p squared divided by 2m dp to the third power. So it's a simple Gaussian integration that we need to perform over there. Okay. So what is this? I assume that you have already seen the Gaussian integral, an integral of this form, e to the minus infinity to infinity to e to minus y squared dy is simply equals to square root of pi. So there is a book, very interesting book about integrations and manifolds and advanced analysis. So in the introduction, the author, which is Arthur Spivak, is a very known mathematician, says how I define mathematicians. So for the mathematicians, the fact that this integral equals square root of pi is the same as 1 plus 1 equals 2 for everybody else. Do you know how to compute this integral? Yes, great. So you are already mathematicians. And in physics, there is a huge number of Gaussian integrals. Huge number of Gaussian integrals, mainly due to the fact that eventually what we try to do is to approximate everything by some quadratic potential, and then everything becomes a Gaussian integral. Okay, so what we have over there is that z equals the volume divided by Planck constant to the third power, and here we have to the third power of what? Of pi, and since it's not an integral over e to the minus y, there is a prefactor of beta by 2m, so it's simply 2m divided by beta, and it equals to the volume divided by the Planck constant to the third power, y squared. Square root, so 3 to the 2. Yes, thank you. This is 2 pi k Boltzmann t m 3/2. This is the partition function of one single particle. Okay, great. If there is something wrong with this result, so it looks nice, right? We don't really have any problems with this result until we start to investigate. And there is something very, very bad with this result. actually it breaks our very fundamental assumptions about thermodynamics. Why? Well, first of all, it's the simplest question. It's the simplest system that we ever had, like the classical ideal gas. All you learn in thermodynamics has roots in this system. Okay. One of the problems, or one of the assumptions that were made on the basis of experiments, and they are postulated into the basis of thermodynamics and statistical mechanics, is that the free energy should be an extensive function. Okay. And what we are going to see, that the free energy of this classical ideal gas, as we obtain it from the Gibbs representation, is not extensive. Okay? So let's write, first of all, let's write the partition function. So the partition function, z, is equal to z to the power of n is the number of particles. Okay? Which is simply v divided by h to the third of 2 pi m k Boltzmann t to the 3 2 over 2 and to the power of n. Okay. The free energy F is minus 1 over beta log of z. So it's simply minus n k Boltzmann t, a log of whatever stands inside. So we have here v divided by Planck constant to the third, 2 pi m k Boltzmann t to the 3/2. This is our free energy. Now, and this guy over here is not extensive. Why it's not extensive? Well, if we take two systems that are exactly the same, has exactly the same number of particles, okay, and has exactly the same volume, and we combine them together, what should happen is that the free energy should grow by a factor of 2. And it won't happen because the volume now, if it's grown by the factor of 2, should be a prefactor of 2 over here. Okay, so it's not a linear function because the prefactor is over here, and there also the prefactor should be over there too. Okay, so we take two systems, each of them has this free energy, we bring them together, the free energy now should be just 2 times the original one, and then we won't obtain this because of this contribution of the volume that sits inside the logarithm. Okay. So, what went wrong, basically? And they had not a clue. So, from the classical perspective, you don't really have a clue what actually went wrong. Well, you had different particles, you looked on them, you calculated the partition function of each particle, and then you obtain a result that is not satisfying your fundamental assumption of the extensivity of the state functions. Now, think of it. So we had a lot of particles, and what we have done, also are the particles in the box. What we have done, we calculated this guy, and we calculated this guy, and we calculated this guy, and we just multiplied all of them. So we used, in order to calculate the different states, so we used the assumption that all the different particles are distinguishable, right? So there are the states of this guy multiplied by the states of this guy, multiplied by the states of this guy, multiplied by the states of this guy. So all the different particles that we had, they were completely distinguishable. What is this not the case? Right? What if the different permutations of all the different particles will produce only one single state? Okay. So I cannot just sum up or multiply the number of states of this guy by the numbers of state of this guy and the numbers of that guy, because if they are indistinguishable, okay, when I perform a permutation, this one with this one, nothing happens because all the particles are the same. So all different permutations of all different particles produces me just no additional states. It's exactly the same state that somehow I counted twice. Right? So the idea, Gibbs, and this is related to the Gibbs paradox of non-extensivity of the free energy, is to say the following. Well, when I computed Z, and I computed this in this form, Z to the power of n, I overcounted. I overcounted different states. What I should do, I should divide it by the total number of the permutations. Why? Well, actually because we will see that this provides us a good answer. This provides us a free energy which is extensive. It's not exactly clear. It's not exactly clear why one should not take care. Why the particles are distinguishable or indistinguishable. From the classical perspective, there is no problem to take this particle and follow it and say those are this particle states and those are that particle states. Right? But still, your initial assumptions and your mathematical derivations force you to say that the particles are indistinguishable. There is no way, or you must treat them as completely indistinguishable particles in such a way as you cannot really follow them. Okay, so what happens if we do this? We divide, or we basically not take into account all different permutations. We treat the particles are completely indistinguishable, as completely that we cannot follow them. This is some sort of a paradox. You cannot follow a particle. From a classical perspective, you can label all of them and track all of them, okay? And they will provide you different states, but the math tells you that you cannot use this perspective. Because if you're using this perspective of distinguishability, you obtain a wrong answer. So let's see, well, what this guy actually does for us. So, if this is true, okay, this is true, the free energy equals to minus k Boltzmann T log of 1 over n factorial multiplied by whatever we have here to the power of n. So it's v h over 3 2 pi m k Boltzmann T to the power of 3 halves, all of this to the power of n, we call the parentheses. Okay, so it is simply f minus k Boltzmann T, okay, and inside we have n log of v divided by h to the third 2 pi m k Boltzmann T to the 3 halves minus log of n factorial. Now, we already used several times the Stirling approximation. So log of n factorial in the large n limit, it's simply n log n minus n. Now, we're going to plug it inside. we're going to plug it inside. And what we are going to get is F equals minus k Boltzmann T n log of V divided by Planck constant to the third 2 pi m k Boltzmann T to the 3/2, okay, minus n log n minus n log n plus n. Okay, still doesn't look very good, but we obtain that F equals minus k dt. Here we have n log of v to the divided by the Planck constant to the third power 2 pi m k Boltzmann T to the 3/2 minus log n. Okay, so there is this guy, this guy, this guy, and we have plus n. Okay, which equals F is minus k Boltzmann T n log V divided by n multiplied by 1 over Planck constant to the third power 2 pi m k Boltzmann T 3/2, okay, minus n k Boltzmann T. So this is the correction that we performed. Does it help us? Yes. Because for the extensivity, the free energy should be simply a linear function of n and v, etc., of the extensive parameters. What are extensive parameters? N and v, in this case, and the volume. So n is coming up linearly here, over here, and over there. The additional contribution from the extensive parameters is this guy, is just simply v over n. V over n is intensive, right? It's simply the density of the particles. So if we take two systems and we combine them together and they have the same volumes, the same number of particles, basically they are identical, okay? So they have the same density of particles inside. We simply need to compute to multiplicate n by 2, v by 2, n by 2, and n by 2, and it turns out that so in total the free energy is simply multiplied by 2. So it works. The question is why it works, A, and why we have to do this thing of treating our particle as indistinguishable. A. There are no answer to this paradox from the classical point of view. Because, well, from the classical point of view, I can take the particle and follow it and say this is the particle and this is the other particles and they're all distinguishable. And this answer to this paradox is actually can be only obtained from the quantum mechanical perspective. Because in quantum mechanics there are two different particles, kind of particles. Okay? There are fermions and there are bosons. So in quantum mechanics, there are fermions, there are bosons. Now, when you write down the equations of quantum mechanics, the Schrödinger equation, and you have identical particles that are identical, they have no labels to them, you cannot just simply switch them. So there are two options in writing your state function. One of them is a symmetrical state function. One of them is asymmetrical state function. Okay. I'm not going to actually derive this representation because you've already seen it in the class of quantum mechanics. But what comes out of it is when your state function is a symmetrical one, all different particles can occupy exactly the same state at the same time. Okay? This is for the symmetrical function. In the asymmetrical representation of the state function, two particles cannot occupy the same state, because then the state function equals exactly 0. Because of the anti-symmetrical way of how it's written. This is the Pauli exclusion principle. So what we obtain from this is that for one kind of particles that are represented by a symmetrical wave function, all of them, they can occupy the same state together. So there is no limitations of how many particles are sitting in a given quantum state. For the other kind of particles, which are called fermions, okay, there is a limitation. The limitation is that 2 particles, 3 particles, 4 particles are never going to occupy the same state together. Okay? There is only one single particle per state. So in quantum mechanics, there are limitations of how particles are counted, how different states are counted. Because in bosons, no limitation for the number of particles per state. For the fermions, only one single particle per state. So if I have different states of my Hamiltonian and I have several particles, the occupation for bosons, okay, if I plot down the spectrum, the energy spectrum, so this is the energy, and it has different levels. There are no limitations of how many particles are sitting per state. So there could be 2 particles over there, 3 particles over there, and 1 particle over here. For bosons. For fermions, due to the Pauli exclusion principle, or anti-symmetric representation of the wave function, if we plot again this energetic spectrum, and we plot again those different energies for the fermions, there is this very strict restriction. 1 particle per level. So there could be 1 particle over here, 0 particles over there, and 1 particle over here. But the situation where 2 particles are sitting at any given specific level is forbidden. Okay. And there is no such restriction for the bosons. So if I'm looking on identical particles, first of all, they are indistinguishable. What do I mean? Here, if I say I cannot distinguish between different particles. If I have particle 1, 2, and 3, they are completely indistinguishable, and I cannot follow them. This is one of the properties of the quantum mechanical. I have this uncertainty principle. If I'm following the particle, I don't know where it's gone in the next time. So switching between particle 1 and 3 at the same state actually does not provide any different state for the whole system. The system is only identified by what? By how many particles, identical particles, are sitting in this state. Not which particles, but how many particles. And this is important. So there is no classical analog for this. This is why I have to treat them as indistinguishable. B, there are some specific restrictions. There are restrictions for bosons, there are restrictions for fermions. Now, when we are assuming that our particles are classical, well, this is an approximation. We can say, well, our particles are like boson-like. They can be in whatever states they want. So the only thing that you should take care of, is those permutations, right? But even this is wrong. And even this is wrong. So the permutations help you somehow, but we will see that it's not exactly right. You cannot say, well, I have classical particles are bosons, and the only thing that I should do is actually say, well, in order for them to behave like bosons, I should divide by the number of permutations. This is also wrong. Classical approximation is approximation, and we'll see maybe why it works. So let's look on an example. Our example is that we have two particles and two boxes. Each box is a state. Each box is a state of the particle. So in classical physics, I have particle 1 and I have particle 2. I don't care that they are exactly identical. I can distinguish between them because I can follow them, right? So all number of different states in classical physics, I have the box, and I can have particle 1 over here, and I can have particle 2 over here. Or I can have particle 2 over here, particle 1 over here. Additional different state is particle 1 over here, particle 2 over here, and particle 1 over here, and particle 2 over here. Different number of states for this system is 4. Number of states. This is a classical system. We take the same system, two particles, two boxes, and look how bosons should behave. So bosons. So bosons can occupy each state, but they are completely identical. They are undistinguishable. Okay? I can switch two particles because remember I told you the wave function is symmetrical. I switch the two particles. Okay? And the wave function stays the same, so it's the same state. But I don't care about permutations. So we have two boxes. One particle over here, one particle over there. If I switch them, nothing happens. It's not a different state. I have an additional state where two particles are sitting over here, and an additional state that two particles sitting over there. So the number of states is 3. Okay, and now we go to fermions. What happens to fermions? So again, the particles are exactly identical. Quantum mechanics. So I can have one particle in one box, the other particle in the second box, and that's it. So the number of states is 1. Number of states. Number of states. The number of states. Number of states is 4. So here I can understand why, because I have the basics. So this is, the number of states here is dictated by quantum mechanics. Here classical physics dictates me that the number of states is 4, and somehow it's wrong. I know that it's wrong. So what I'm doing, I'm saying, well, let's divide all of this by the different number of permutations. So the corrected number of states is what? Is 4 divided by n factorial. How many particles I have here? 2. Let's divide it by 2 factorial. And I get the answer 2. So what are those classical particles? Bosons? No, bosons have exactly 3 states. Fermions? Fermions have only 1 state. I have something in between. It's not that I actually, by dividing by this total number of permutations, it's not that I actually now got the right quantum mechanical statistics or quantum mechanical behavior. No, I simply introduced a factor that corrects something and brings me closer to the truth in my representation of the free energy than it was before. But it's not that now I got exactly the boson statistics or the fermion behavior. My particles are still classical particles. They're distinguishable, there are different states, etc., etc. I must correct it somehow, and it appears to work. Now, why it's actually working? Because I have seen that I haven't done any transformation that brought me exactly for bosons or fermions. This simple example shows that this transformation does not work. It's not that I obtain boson statistics, fermion statistics. What actually happens is that classical physics works only in the high temperature regime. In the high temperature regime, the situation where one state is occupied, exactly one state, is occupied by 2 particles, it's pretty much negligible. Okay? So we have a lot of states. We are up there in the spectrum. Our temperature is high. So each different state is only usually occupied by 1 single particle. There's a lot of states, and there are no situations, or the probability for a situation that 2 particles, either bosons or either classical states, they always, in the classical limit, I'm sorry, the same state is never occupied by the same by 2 different particles. So only in this limit, when the temperature is high enough, the classical representation, the boson representation, and the fermion representation, okay, they all show exactly the same result. Because I don't care about those states, I care only about those states, and I divide it by the number of permutations, which only works over here. Okay, so I should get 1 state for the classical, for the boson, and for the fermions. And only because of this it works. And if we are trying to apply classical physics in the low temperature regime, it won't work because, well, then those states are becoming important. Either they are occupied or either they are not. And then I will obtain a different result from the boson perspective, bosons and fermions. So the classical limit works only in the high temperature and should be corrected because of the indistinguishability. And the indistinguishability comes purely from quantum mechanics. So, okay, so we are continuing with our tale about classical representation of the partition function. And what we have noticed that, in order to escape this paradox, Gibbs paradox, we must divide our partition function by the number of permutations. Now, how it works if we have different systems. So, if we take one system that has n1 particle and has and they are not interacting, the particles are not interacting. So if we have z1, which is equals to 1 over n1 factorial z1 to the power of n, and we have for the second system z2 should be 1 over n2 factorial z2 to the power n2. Z, the partition function of both of those systems, is just the multiplication because it comes from the summation of different states. And we assume that there is some sort of a factorization because They are not interacting. If they are interacting, there is we cannot just multiply them together. So it's simply z1 multiplied by z2, and it's simply 1 over n1 factorial z1 and 1 multiplied by 1 over n2 factorial z2 and 2. This is usually how you proceed in all different situations for the classical representation. You always should keep in mind that you have to divide it by some factorial, which is basically a crude classical attempt in order to escape the problem of extensivity, okay, as we see it. It only works for high temperatures. When we go to low temperatures, there is no way of escaping quantum mechanical representation. You should choose your system wisely. Either you're treating bosons, either you're treating fermions, and we come to this later. And as we see that there is some specific restrictions, conditions on the total number of particles, and how the total number of particles behaves, and how this total number of particles can occupy the different states. We will see it a little bit later. Maybe not today, maybe tomorrow, but we will see it and how it comes into play. Those two different behavior of quantum particles. Now, still on the frontier of classical physics, something actually pretty interesting is occurring for high enough temperatures. Because when the temperatures are high enough, we can take the classical representation. Let's see what happens. Let's see what happens if the energy that is contributing to the energy can be represented as some constant multiplied by p squared. So we are looking on one particle, one dimension. This particle have in his energy a quadratic term that is coming from the kinetic part, and as physicists always like to do, we have also a quadratic term that's coming from its potential part, a q squared. So if we have only this particle and it has those degrees of motion, so it has a potential energy and it has a kinetic energy, okay, how its partition function is going to look, A, and how its heat capacity is going to look too. Okay, so I'm trying to actually derive a way to count different degrees of freedom, different degrees of motion for high temperatures. And as we would see, that in any case that we have energies that are of those quadratic forms, the same we've seen in Debye and in Einstein model, we would see that there is a constant contribution from each degree of freedom that is entering into the heat capacity. And basically by looking on heat capacities, you can understand a lot about what's going on for different molecules. So let's see in this classical picture how first the partition function looks like, and afterwards how the heat capacity looks like. Okay, so this one single particle, the partition function of this guy is an integral of e to the minus beta h dp dq. Okay, so it equals to divided by 1 over h constant, h, the Planck constant, 1 over h. Okay, now, so it's 1 over h, an integral from minus infinity to infinity, minus infinity to infinity. We assume that the potential is bounding potential, okay? This a is positive. So we have e to the minus beta b squared plus a q squared dp dq. This is equals to 1 over h. The first integral is integral from minus infinity to infinity e to the minus beta b squared dp, and an integral of minus infinity to infinity e to the minus beta a q squared dq. Okay, so we have a simple multiplication of Gaussian integrals. Okay. Each of them is simply computed. We already have seen, or we seen what is the result of the Gaussian integration. So this guy is the square root of pi divided by beta b, and this guy is the square root of pi divided by beta a. We really don't care about b and a over here. The beta contribution is important, so we have 1 over the Planck constant, square root of pi squared divided by b n multiplied by k Boltzmann t. So we have some sort of a prefactor, and you'll see that we don't care about it. This is z. And we have a k Boltzmann t contribution. Okay. Now what we actually want to compute again is the heat capacity. It's easily measured. People thought they understand everything by measuring heat capacities. So what we are going to compute is the heat capacity. But the thing to notice is, in any case that in our Hamiltonian stands a quadratic form, it contributes each part of this form. So for each degree of freedom, the degree of freedom here, P is 1 degree of freedom, Q is 1 degree of freedom, each of them contributes a k Boltzmann t to the power 1/2. Okay? No matter how many degrees of freedom do we have over here. Why? Because, well, we can do the following thing. In general, the partition function is z1 over n factorial, 1 over n factorial, z to the power of n. Okay. So it equals 1 over n factorial, 1 over h bar, square root of pi squared dA k Boltzmann t, all of this to the power of n. Okay, so let's look like what is the free energy looks like. It's minus k Boltzmann t log of z, and it's simply minus k Boltzmann t minus k Boltzmann t. Here I would have log of 1 over n factorial, 1 over h bar, square root of pi squared b a k Boltzmann t to the power of n. Okay. Now, eventually, what I have here is minus k Boltzmann t, minus k Boltzmann t, I'm sorry, log of n factorial, plus again a k Boltzmann multiplied by n and the log of whatever stands inside, so it's 1 over h square root of pi squared b to the a. Okay, all of this multiplied by k Boltzmann t. And in addition to this, what I have is, this is minus, plus, minus, minus, and I have minus k Boltzmann T, n and a log of k Boltzmann T. So this is my free energy. All right. This is my free energy. Okay. I can even write it down as f of k Boltzmann T multiplied by some function, which is not dependent on t, minus k Boltzmann T multiplied by n and log and k Boltzmann T. Okay. Now I remember that the entropy is simply minus dF to dt, and my heat capacity is T ds to dt when the volume is kept constant. Okay, so what I need to do, first of all, I should take the derivative with respect to t once, okay, and I obtain that S is minus k Boltzmann multiplied whatever I have inside, okay, and here I have something which is different. So first of all, I have plus k Boltzmann T and log of k Boltzmann T, right? So I'm taking the derivative of this guy and I'm multiplying it by minus, okay? And the other one is plus k Boltzmann n. Yep. K Boltzmann n. Okay, this is the only thing that I have left with. Okay, this is S. Now I'm going to compute the heat capacity, which is again just taking additional derivative with respect to T. Volume is constant, so the number of particles is constant, everything is constant, so CV is n multiplied by k Boltzmann. This is my result for particles that they had potential energy, harmonic potential energy, okay, or their potential energy was basically a quadratic function, and their kinetic energy was a quadratic function. The kinetic energy is always a quadratic function. The kinetic energy is always a quadratic function, but the potential energy sometimes is quadratic, sometimes it's something else. And in general, when we're going to very high temperatures, we don't really care about the potential energy at some point anymore. But what I want to show you that, well, what we had here is k Boltzmann T multiplied by k Boltzmann T. So this guy I can also write as what? CV equals to n multiplied by 2 multiplied by 1/2 k Boltzmann. So I started that I had two contributions to my general energy. Each of them were quadratic. Each of them contributed 1/2 k Boltzmann. In total, I had just k Boltzmann, and I multiplied it for all different molecules that I have in the system. So this is this behavior of the heat capacity, what is called equipartition theory. What it means? It means that if you have a degree of freedom, and this degree of freedom, okay, is described on the energy level by a quadratic behavior of the energy, this degree of freedom is going to contribute exactly 1/2 K Boltzmann to the heat capacity. Okay. So if you're looking on the heat capacity for high enough temperatures of different molecules by actually counting how many K Boltzmanns I have over here, halves of K Boltzmanns I have over here, I can actually understand what are the different degrees of freedom are there for my molecules. Okay. Because think of it. When I have particles, where my molecules are just particles inside a box, and this is a three-dimensional box, what the equipartition theory tells me? The equipartition theorem tells me, well, you don't have contributions to your potential energy. You're just a free guy. So your potential is just a sum over all your particles of bi squared. You don't care about the prefactors. You only care about I goes from 1 to n. Okay. Your pi is actually 3 degrees of freedom. 3 degrees of freedom. You have a momentum in the x direction, in the y direction, and the z direction. So CV, according to the equipartition theorem, is the number of particles multiplied by 1/2 kb for each degree of freedom, and you have 3 degrees of freedom over there. Okay? So for the particles that they have only translational degrees of freedom, a gas of particles, what we obtain? We obtain that it have exactly 3/2 kb Boltzmann. So when we're looking on the I'm sorry, when we're looking on the CV per mole, okay, when we're looking on the CV per mole, what we obtain is that for high enough temperatures, for particles that have only translational degrees of freedom, we're approaching CV per mole. We're approaching a quantity which is simply R multiplied by 3/2 K Boltzmann. Okay. So this is your quality. Now, when you can measure it, you can measure your heat capacity, and you compare it to your prediction. You're saying, well, this is exactly what I have got. So I have their particles with only translational degrees of freedom. Now, what if, for example, your particles have x direction, y direction, z direction for their momenta, but they can also rotate. So those are molecules that, well, they're not exactly circle. They don't have a circle symmetry, but so they can rotate in the theta and in the phi direction. So they have 2 additional degrees of freedom. Okay, so they have 2 additional degrees of freedom. In this case, when they can also rotate, what you expect is that your CV will have what? So CV is again n multiplied by 1/2 kb by the number of the degrees of freedom. So we have 3 translational degrees of freedom moving in x, y, and z. It's again particles in a box. They don't have any potential energy. Plus 2 rotational degrees of freedom. Great, so what we obtain, that CV per mole equals R multiplied by 1/2 or 5/2 K Boltzmann. So if I'm looking on the heat capacity and it's for high enough temperatures looks like this, okay, I can say for sure that my molecules are not only moving translationally, they're also rotating. Each degree of freedom per molecule adds additional 1/2 kb. Now think of it that my molecules are actually combined from two molecules. Okay. Okay. So my molecule looks something like this. But actually, inside my single molecule, I have two molecules, two atoms, or two something, okay, that can, well, the molecule as a whole, moving translationally, rotating, okay, and in addition to this, okay, the two sub-constituents of the molecule can vibrate, okay, and move along. So the vibration, for example, the vibration can also add me an additional degree of freedom. So for such molecules, what I obtain, that CV per mole is R multiplied by 1/2 KB multiplied, in this case, already by 6. Okay? And I can continue with this, etc., 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 etc. First of all, what it tells me that if I obtain some specific constant heat capacity, I can know what are the constituents of my gas or my substance that I've been measured for high enough temperatures. I don't need a microscope in order to actually go inside and say, well, this molecule have this such and such degrees of motion, degrees of freedom. I can compute the heat capacity, okay? I can assume the equipartition theorem that each degree of motion is contributing 1/2 kb. I can assume that it has translational degrees of freedom, vibrational degree of freedom, rotational degree of freedom, the degree of freedom of each of those constituents to move as they wish, okay? And this is how I can compute, and then I can say, well, I have 7 degrees of freedom there. The molecule is such and such, okay? Even more, I can change the temperature and get from one plateau, okay, as a function of temperature, looking on the CV, I can observe such transitions. So it would be a constant for 0, constant for pretty long period of the temperatures, and I can go jump up and be again constant. What happens over there? The step size is quantized. How? By 1/2 kb or 3/2 kb or 4/2 kb. What happens? So at this specific temperature, I can say that this is the vibration. For low enough temperatures, the molecules are moving like rigid small bodies. Nothing is really vibrating inside. Okay? So I have only a specific number of degrees of freedom, because all the additional degrees of freedom, they're frozen out. Okay? It's too cold for them. The particle is barely vibrates. I can neglect all those degrees of freedom. Okay? I increase my temperature above a specific threshold, then vibration kicks in, okay, and I obtain a different CV. So I can go now and assume something about the interactions inside the molecule itself by learning how this stepping process actually occurs. It's not a quantum physics now, okay? But those steps are occurring specifically due to, well, here something is frozen, here it's already not. What is this something? Degrees of freedom. The degrees of freedom are quantum numbers or integer numbers. I can have 1, 2, 3, 4, 5. I can never have 4.6 degrees of freedom. So I have integer steps. Great. Now, they observed this, guys. They observed this stepping, and they also observed the constant values of the heat capacities way before they understand anything about how matter is actually made, that it's made of atoms, and that there is some quantum statistics, etc., etc. From the classical perspective, I can say, well, what are the degrees of freedom? I can divide my matter to smaller and smaller particles. Okay, smaller and smaller volumes, and each volume is a degree of freedom. So there is infinite degrees of freedom from the classical perspective, because there is no limit for how much I can divide my system into how many particles, if everything is continuous. Okay, now then the heat capacity according to the equipartition theorem should go to infinity, right? Because I will say, well, I have an infinite number of constituents inside my system, an infinite number of degrees of freedom, so the heat capacity should go to infinity. And it's not going into some infinity, it goes to a constant, and this basically says that there is a limit. So there is a number of specific number of particles inside your system. Again, you can understand the atomic structure from a very classical perspective. Okay, so this was the heat capacity. And again, from looking on the behavior of the heat capacity with the temperature, we can learn something about how many degrees of freedom per molecule we have in the system. Okay, our next theme is disorder and entropy. So, how we define the entropy? We define entropy as K Boltzmann log. So, well, it actually depends how we define entropy on what ensemble we were using, right? When we started to talk about statistical mechanics. Beforehand, we had no definitions for the entropy. The only thing that we knew about entropy is that according to the second law of thermodynamics, how we define it, entropy is some function of the state of the system, and it grows. Okay, it has its maximal value. So, and we use this maximization principle in order to derive different stability relations, in order to use it for describe the phase transitions in the thermodynamic element. In the microcanonical perspective, we accounted for the entropy and the number of states, right? Now, again, there was some problem with extensivity, so we used, in the microcanonical perspective, if omega, the number of states, so it's microcanonical ensemble. So if omega, big omega, was the number of states, the entropy was K Boltzmann log of omega. And we have shown that this definition of the entropy satisfies whatever we've been using in our from the thermodynamical perspective. Okay. Now, in this case, we also define the different probabilities of being in state I. So it's probability of being in state I. So what was Fi? Well, the energy in microcanonical ensemble is constant, exactly constant, and the probability of being in each of these accessible states is exactly the same. So Fi is simply 1 over omega. Okay. This is great. Now, how the entropy is now defined in the canonical example. Okay, what is entropy? So we have canonical ensemble, and what we have used there in the canonical ensemble, if you turn a couple of pages, you would see the only thing that we define there is actually the probabilities. Those FIs, right? You remember the number of states in the reservoir, okay, divided by the total number of states. What the number of states of reservoir that are associated with a specific state of our system. Okay, and what we have shown that Fi was e to the minus beta ei divided by z. Z is our partition function, whereas z is a sum over I e to the minus beta ei. Okay, this was our starting point, and this is the main result for the canonical ensemble. What about the entropy? Okay, how entropy looks like. So we know that the free energy F is E minus Ts. So S is 1 over T multiplied by E minus F divided by T. So if we know how to compute the free energy, and if we know how to compute the energy, and what is the energy over here? The energy is the average energy. We can compute our entropy right now. So we know how to compute the entropy of the whole system, reservoir plus our specific system. But the entropy of our system, we should use this formula. Okay? Because the energy is fluctuating right now. And here we're using the average energy. Okay, so first of all, the free energy is minus k Boltzmann T log of z, right? And E is simply a sum of I, Fi, Ei. E is the average energy. Free energy is defined. We already seen that it's defined like this. Okay. So what we obtained? We obtained that the entropy in this case is what? The entropy is 1 over T sum of I, Fi, Ei plus K Boltzmann log of z. Okay. And I would rather write it as K Boltzmann multiplied by beta sum of I, Fi, Ei plus K Boltzmann log of z. So this definition of the entropy for the canonical ensemble a little bit looks different, at least for us, than the simple definition in the microcanonical case. Now, how the entropy is related to disorder. And what is disorder? We mentioned the disorder quite a few times during these lectures. But how we define disorder? So if I'm looking now on the squares over here, they look quite the same, and they are somehow ordered. There are 2 and 1/5 of a plate over here, and it's the fabric looks nice, and it looks like everything is ordered by somehow and somehow. So there was a law, and according to this law, those piles were put on the floor. In the poker game, the order is if I have a specific hand. So for example, going a flush, straight flush, it looks like ordered. Or I have 4 kings, it looks like something it's ordered. The same pattern repeats itself. So this is usually how we associate order and disorder. But, you know, take some impressionist artist and you have a very nice picture that you have no clue what it's actually plotted inside there, but it's have a very precise order for the artist who made it. You take one specific component out of it and everything falls down because everything has its place, has its order. you don't know the laws. This is why you don't know what is order and disorder, but it also can be ordered, although to you it doesn't look like. So in order to speak about what is ordered and what is disordered, you need to define specific laws of what is order with respect to what. Now in statistical physics, when we speak about order and disorder, we speak about the different distributions of the system to participate in its different admissible states. Okay? So for us, order or disorder is the capability and the distribution of the probabilities of the state of being in, of the system of being in its different states. It's basically, when we talk about order and disorder, we talk about the different distributions of the FIs. Okay? So what is an ordered state? Well, the ordered state for us would be that the system sits in exactly one state and it has zero probability of being everywhere else. It doesn't matter how the system looks like, but this delta function probability of being in a one specific situation is an ordered state for us. Okay. The disorder would be that it has some probability of being here and the probability of being in this situation and the probability of being in that situation. This is a disorder. An order where there is only one specific state. It can be very, very, very awkward, but it's one single state. Now, why we actually understand this in this way? This is due to Claude Shannon. We're talking about the 40s. And Shannon was working on information theory. And in information theory, you have to define what is order, what is disorder. So from Shannon's works, we now have a postulate of what we call disorder, what we call order, with respect to the different probabilities of being in different states. So you have, your system has different states, and it can be in each of one of them with specific probability of Fi. With respect to those probabilities, you have to define your disorder that will satisfy a specific mathematical postulates. So what are those mathematical postulates or requirements? Okay. So A, the measure of disorder is defined only by your FIs. So it's only the distribution of your probabilities. This is the only thing that should define your disorder. B, if any of Fi equals 1, the disorder is 0. Okay? You should define what is the zero disorder, what is the most ordered state. The most ordered state is that you have a one single probability of, you don't have probabilities. You are certainly sitting in a specific state. See, what is the maximal disorder that you can have? So, maximal disorder is achieved when Fi equals 1 over omega. Omega equals number of states. So think about it. If you don't care where to be, you have 30 possible states, okay? And your system can choose any one, any of them, with exactly the same probability of 1 over 30. According to Shannon, this is the maximal disorder that you can have. Because you do not have any specific situation or any specific areas where the system is plausibly to be found. It can be anywhere. So from Claude-Shannon perspective, this is the most disordered state, situation. The situation with the most disorder. The maximal disorder is an increasing function of omega. The more states you have, your maximal disorder should grow. Now your disorder is a function, right? So A, B, C, D, E. Yeah, this is right. E. If for subsystem 1, the disorder equals this one, and for system 2, the disorder equals this 2, disorder equals to F1 this 1 plus F2 this 2, where Fi probability of being in subsystem I. This is something that's related to extensibility of everything. So this, if you want to define disorder, according to some information theory postulates about how many disorder, how many information that you have about the system, which is related to a lot of cool concepts, you should have all these 4 requirements to be satisfied. Now, what you can prove is that actually the form of the disorder that is satisfies those requirements is disorder equals to minus k sum over fi log of fi, where k is some positive constant. This is your disorder. So disorder that satisfies these requirements, the only thing that you need to know are the different fi's, is defined by this guy. Right, so let's take, for example, that there is only one single fi, it equals 1, the disorder is exactly 0. Right? What happens? So, what happens when fi equals 1? There is one specific fi that equals 1. So disorder equals to minus k sum of 1 log of 1, it equals exactly 0. Very simple. Now what happens when fi equals 1 over omega? The maximal disorder. What is the maximal disorder for a given system? So the maximal disorder is minus k sum over 1 over omega log of 1 over omega. It's a sum of 1 over omega k, a sum of log of omega. What is the number of states? It's just omega, so it equals k log of omega. This is very interesting. Why? Because we know that for a microcanonical ensemble, the entropy is exactly log of omega multiplied by a very specific constant, the K Boltzmann. So for microcanonical ensemble, S equals K Boltzmann log of omega. It's the same omega as the number of states. So what we see, that the disorder or the maximal disorder that is possible for this system is exactly the entropy when the system is closed. What is a microcanonical ensemble? Where our system is isolated. Okay, so if we are treating or trying to treat the disorder or the entropy of a closed system, for any kind of distribution, for any kind of situation, the entropy of a closed system is the entropy which is corresponding to the maximal disorder that you can have for the system. Okay. So your equilibrium, because this is your equilibrium of your system is closed and the entropy defines all your different states, your equilibrium is actually appears when your entropy is at maximum. And we already know this. This is the postulate. This is the postulate of thermodynamic laws, right? We already know that. We already seen this in a little bit of a different perspective, but it's the same. The same claim. You can look on the entropy. You can look on the and you associate the entropy with the disorder. Okay. You can associate your entropy with the disorder of the system, and then you can ask yourself, what is the equilibrium for this closed system? And the answer is when your entropy is maximal, when the disorder is maximal. Okay. So in general, you can go and say for a closed system, I can always associate my entropy as minus KB sum of I, Fi, log of Fi. I can say, beforehand, I only defined the entropy for some equilibrium situation. I can say, well, no, I can associate the entropy with any kind of situation. But in equilibrium, this guy goes to maximal, and there is a one specific answer. S equals to K Boltzmann log of omega. Okay. So what we have seen, that for the microcanonical ensemble, maximization of the disorder and association of the disorder with the entropy, this is what actually produces the equilibrium situation. In order to answer what is the equilibrium for a closed system, we can ask what is the maximal of the disorder of the maximal of the entropy when the entropy defined in this way. Now let's see if we can make the same claim or some similar claim about a different kind of system. So microcanonical ensemble, there were no constraints. It was a completely isolated system. A canonical ensemble is an ensemble where the temperature is constant. So we have a reservoir and we have our small system on what we assume that the temperature is constant everywhere. Okay. Another thing that we obtain for constant, that the average energy of our system, okay, not the reservoir was a system, but the average energy of our system was constant. Okay. So let's see what happens in the canonical ensemble. In the canonical ensemble, for the disorder, when we have the assumption that E, which equals to sum of I, Fi, Ei, is constant. I want to see what happens to the disorder which equals to the minus k sum of I, Fi, log of Fi. Okay? What is the maximal disorder for this system, for the canonical representation, when the energy is kept constant? And can I again associate this disorder and this representation of the entropy with the regular entropy that I have? Not that I, from the beginning, define this is my entropy. But what I want to do, I want to define a disorder, find its maxima, and to show you that exactly as in the case of microcanonical ensemble, the maxima is the value of the entropy, the maximum of disorder is the value of entropy, the same is going to happen for the canonical ensemble. Okay? So what I want to do, I want to write the disorder, and I want to find its point when it's maximal. Okay? So the disorder is, so disorder is minus k, a sum of I, Fi, log of Fi. Okay, this is my disorder. I want to take a variation of this, so a delta of minus k, sum of I, Fi, log of Fi, and I want to compare it to 0. Okay, so this is some general function. I have a lot of different probabilities, Fi's. They can be somehow correlated. We'll see how exactly. And I want to find the exact situation when this guy is maximal. So I have a lot of variables. What are my different variables? The Fi's are my variables. Okay? And I want to find exactly the specific point. What are the values of all the different Fi's when this guy gets maximal? Okay, so what is this variation of? It's basically minus k, sum of I, delta Fi, log of Fi, okay, minus k, sum of I, Fi multiplied by 1 over Fi, delta Fi. This is all equals 0. So it's like taking a differential of this equation, but I'm using deltas instead of the differential. That's it. So let's take the deltas out. So we have minus k, sum of I, log of Fi, plus 1, multiplied by delta Fi, all of this equals 0. Okay, so this is the equation that should define the maximum of the disorder. But there are constraints, right? Because, well, I cannot just say, well, this equation is always satisfied when what? When the guy in the parenthesis, this term, equals 0. Because all the different Fi's are constrained. Okay? What kind of constraints do we have? So first of all, we know that sum of I, Fi equals 1. This is the first constraint. What is the other constraint? The energy is constant. Okay? What is the other constraint? The other constraint is sum of I, Ei, Fi equals constant. The average energy of the system is constant, canonical ensemble. So we need to solve this equation under those constraints. So what is the way to do it? Lagrange multipliers, right? Because if we take delta of sum of Fi, it equals a sum of delta Fi, and it equals 0, right? Because the variation of the constant is 0. The same goes for the other constraint. So the delta of sum of f of I, ei, fi equals to sum of I, ei, delta fi, and it equals 0 because it's always constant. I just have taken a derivative of the constant. I can use the language of Lagrange multipliers. What is the language of Lagrange multipliers? Instead of solving this equation under those two constraints, I'm going to directly introduce the constraint into this equation and solve it without any constraints. Okay, so I have minus k, sum of I, log of fi plus 1, delta fi, minus lambda y, sum of I, delta fi, minus lambda 2, sum of I, ei, delta fi, and all of this equals 0. This is my equation that I need to solve without any constraints. Okay. So what I got over here, I can take the k's out, and because those are constant that I still haven't derived what are they, so I just can take the representation here as minus lambda 1 k, and here I will have minus lambda 2 k. I don't really care about this k. And I have minus k, sum of I, log of fi, plus 1, plus lambda 1, plus lambda 2, ei. Delta fi equals 0. The variation of all the different fi's are uncorrelated right now. No constraints. So in order for this equation to be satisfied, we need that log of fi plus 1 plus lambda 1 plus lambda 2 ei equals to 0. What is the solution of this? Fi equals to an exponent of 1 plus 1 lambda minus 1 minus lambda 1 minus lambda 2 ei. How we know what is lambda 1 and lambda 2? Well, we know that a sum of I, fi, equals 1, which basically says that a sum of I, e to the minus 1 minus lambda 1, e minus lambda 2 of ei equals 1. And we know that the sum of I, ei, fi equals e, okay, which basically e to the minus 1 minus lambda 1, sum of I, ei, e minus lambda 2 ei equals e. So in order for this to be satisfied, and this guy is simply so we can show that e to the minus 1 lambda 1 it equals 1 over e to the minus lambda 2 ei, so we obtain what? That 1 over a sum of I, e to the minus lambda 2 ei multiplied by sum of I, ei, e to the minus lambda 2 ei, all of this equals to e. So we choose lambda 2 to be what? It's a sum specific constant. 1 over k Boltzmann T. E to the minus 1 plus lambda 1 equals to 1 over a sum of I e to the minus beta ei. This is very simple. But what we have obtained what we have obtained over there. What we managed to obtain is that the Fi is equal to what? The Fi is equal to e to the minus beta ei divided by z, where z is a sum of I e to the minus beta ei. The exact definition of the canonical ensemble. So the maximization of the disorder under the constraint that the average energy is kept constant provides us exactly the distribution of the distribution of the canonical ensemble. So again, and if we now associate the disorder equals entropy, okay. If we now again associate the disorder that it equals to entropy, and we can actually do this, how? Okay, we should take this definition of Fi, K Boltzmann Fi, and if we can obtain that the disorder is associated with the entropy, what we can obtain is actually again the same principle. That we should take the entropy, maximize it, and this exactly one single point when the entropy is maximal, this is what provides us the equilibrium distribution of the canonical ensemble. And if we apply it to microcanonical ensemble, again the maximization of the entropy provides us with the the distribution for the microcanonical ensemble. It's always the maximum of the entropy. So let's see if we can actually say that the disorder equals entropy. So what is the disorder? The disorder is minus k sum of Fi log of Fi. What it equals to? Minus k sum of e to the power of minus beta ei divided by z log of e to the minus beta ei divided by z. It equals to minus k sum of I minus k sum of I e to the minus beta ei divided by z multiplied by minus beta ei. So let's do stepwise. So it's log of e to the minus beta ei minus log of z equals to, right? It equals to minus k sum of I. This guy is minus beta ei e to the power minus beta ei divided by z, okay, minus log of z sum of I e to the minus beta ei divided by z. This equals to k beta sum of I ei multiplied by Fi. Why? Because e to the minus beta ei divided by z is simply Fi. Okay? Minus k log of z sum of I I. So we obtain K beta E, because this is the average energy, minus K log Z. Now, if K equals K beta, what we obtain, that is K Boltzmann beta E minus K Boltzmann log of Z, and it equals exactly the entropy that we had before for the canonical ensemble. I think I erased it already, but this is exactly the entropy. So we find a new law, or a representation of our ensembles. What is this, our representation? Okay. Instead of saying, well, we have this, and this is equals, those are specific probabilities, and those probabilities should be equal to this and that because of some other concept that we already introduced, we can say, look, you need to take your entropy that is defined by your disorder, which is this Shannon entropy, sum of KB log pi log pi, minus. You should take this constant K to be equal to the K Boltzmann, and you should find your maximal values of this disorder, or maximum values of your entropy for a specific situation. When the situation that your system is closed, okay, and it has no interactions with anything else, it's a microcanonical ensemble, and the maximal entropy is when the probabilities are 1 over the number of states. Great. When your system is not closed, but actually what is your constraint is that your average energy is constant, what you obtain that your probabilities are those probabilities. Probabilities that we already obtained for the canonical ensemble. And now what we are going to show next lesson is when you're saying, well, I want not only for my energy to be constant, I don't want only for my energy to be constant, so E is sum of I, Fi, Ei, but actually I want that my system can exchange particles with the reservoir. And the only thing that I want to be constant is the average number of the particles. Sum of I and I, Fi. For this state, I have this amount of particles. For that state, I will have that amount of particles. Now, we can use again this formalism of maximization of entropy when we define the entropy as a disorder. And what we obtain, that for this Fi equals to e to the minus beta Ei minus mu Ni divided by Z. And what is the partition function in this case? The partition function is a sum of I e to the minus beta Ei minus mu Ni. We will show it in the next lesson. And this is the grand canonical ensemble. Grand canonical ensemble. And we can obtain all different kinds of ensembles. We can obtain average pressure. We can obtain average magnetic field, or whatever average what we want there. Instead of saying we are very, very much constrained, this is the closed system, the same way as we done in microcanonical ensemble, and this is very hard to compute. We're saying, well, let's make the system to exchange energy. Let's make the system to exchange particles. Let's make the system to exchange all other different properties with the environment. What kind of statistics describes the system now? And we can use this maximization of the entropy in order to define what is my equilibrium. Remember, it's only in equilibrium. We beforehand defined the entropy in equilibrium. Now we're defining entropy in any situation, but we are saying what is the entropy in equilibrium. This is the entropy that maximizes the disorder. From this, we obtain this, our statistical description. Okay, we end up here. See you in 2 weeks.